In this next tutorial, we will be able to describe the three situations where a limit does not exist. So if you'd flip over to these three examples on our notes, I'd like to illustrate the three examples where limits do not exist, first of all graphically, and then I'll show you verbally. First, I don't want you to think that these do not exist simply because I cannot plug a zero into this denominator. In the first tutorial, we calculated two limits in our calculator that did exist even though we could not plug the number in. It has nothing to do with that. But I'd like to look at the visual of what this graph looks like, the absolute value of x divided by x. And I'm just going to plug in some values. I'll do 1, 2, 3, 4, and -1, -2, -3, -4. So if I plug in a 1, well, first of all, I can't plug in a 0, of course. If I plug in a 1, the absolute value of 1 divided by 1 equals 1. If I plug in a 2, the absolute value of 2 divided by 2 is also equal to 1. If I plug in a 3 and a 4 and a 5, I'm going to get 3/3, 4/4, and 5/5, which is also equal to 1. I cannot plug in a 0, so I'm going to put an open dot there, but everything else in the positive direction will be this nice constant 1. If I try to plug in some negative values, the numerator will continue to stay positive because it's the absolute value, but the denominator is going to change the signs all to -1. Again, I cannot plug in a 0, so I'll do an open dot, but this left side, where all the negatives are, will be a constant -1. So this is what our graph looks like. And this limit does not exist. I'm going to use D and E for does not exist. And the explanation for this is as x approaches 0, the limit does not approach the same thing. On the left side, we are trying to approach this open dot of -1. On the right side, we're trying to approach this open dot of +1. We cannot approach two different values. Look at your definition of limit. The definition of limit says we have to approach one value L. So that's the first case where the limit does not exist.
The limit does not exist. The limit does not exist.
Our second case, again, I cannot do direct substitution, but that doesn't mean the limit doesn't exist. It's because of the graph of what this looks like. Let's graph this one. We know that there's a vertical asymptote at x equals 0. Because the vertical asymptotes come from denominators. There's actually a horizontal asymptote at y equals 0 because of the degrees. And if we graph this using our table or using our calculator, this part will look like that, and this part will look like that. So we've graphed those before. Let's see why this limit does not exist. D, N, E. Well, as we get closer and closer to 0, let's look on the left side. As we get closer to 0 on the left side, it looks like our function is going up to infinity. And on the right side of 0, as we get closer and closer and closer, it also looks like the function is approaching infinity. So we're not approaching two different values, we're approaching the same value. So what's the problem? Well, the problem is positive or negative infinity are not numbers. And our limit definition clearly says we must be approaching a number L. Infinity and negative infinity are concepts. They are not considered numbers. So when we are increasing without bound, or sometimes we'll be decreasing without bound down to negative infinity, that limit does not exist because those are not numbers.
What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist.
Let's look at our final example, the sine of 1 over x. Obviously, we can't plug in a 0 because we can never divide by 0. I don't know what this function looks like, so I'm going to use my calculator to illustrate this one. So pull out your calculator. Let's go to y equals and type in the sine of 1 divided by x. Enter. And let's graph that. I'm already on zoom 6, which is our standard zoom. And okay, now obviously I'm very interested in what's happening very close to 0, and we can barely see that. So what I'm going to do is press zoom and then in number 2. So zoom in, and I'm going to press enter to zoom in, and it'll get a little bit closer. And I can see that the graph's doing, okay, that's kind of weird. And let's zoom in again. I'll press enter again, and it's going to get even closer to 0. And okay, now this is very interesting. The graph's going crazy here. I'm going to do one more time, one more zoom. And you're going to see that basically what's happening is this graph cannot decide what to do. It is bouncing back and forth between +1 and -1. And the closer we get into 0, the more crazy it becomes. So let's do a quick sketch of that. So clearly the graph is doing this and then this. Yep, that's about right. That's exactly what the graph's doing. And this graph does not have a limit, at least not when x is approaching 0, does not exist because the graph cannot oscillate. And that's the vocab word that we learned from this one. The graph cannot oscillate. Like I said, what happens is as we're getting closer to 0, the graph is bouncing back and forth between +1 and -1. It cannot decide what to do. And that's called oscillating. So this is the third example for why a limit does not exist.
The limit does not exist. The limit does not exist.
I'd like you to get to know these graphically like we've just done, and verbally. Limits do not exist. Number 1, if f of x approaches different values, that's no good. Number 2, if f of x increases or decreases without bound, that's your plus or minus infinity idea. That's no good. Or number 3, if f of x oscillates between two values. Those are the only 3 times where a limit will not exist. Any other time, I would try direct substitution first. And if I cannot do that, then right now we'll use a table. Thanks for watching this quick tutorial, and I'll see you in the last one. And we'll practice this in class. See ya.